Hello, geometry. I'm going to attempt to do a little bit better explaining this 9.4 section. And some of this that I'm going to go over right now is stuff that I was able to somewhat successfully do in sixth period last Friday, but I thought it'd be good to start from scratch. So we've already talked about an altitude, which goes from vertex perpendicular to opposite side. When it's drawn to the hypotenuse of a right triangle, it does create some similar situations with your triangles. And these are your similarities. You have three different similarity statements because we have three different triangles. We have the big triangle, and then we have the little triangle on the left, and then we have the little triangle on the right. And with those three triangles, we have three different similarity possibilities. And you could, if you want to memorize the similarity statements, you could. I think it's a little bit dangerous. And so I'm going to attempt to explain this in a little bit more detail. Maybe a little bit more clearly how we can generate those similar triangles without having to rely on rote memorization. So what I have here is a huge right triangle drawn. And in every right triangle, you should know that the acute angles are supplementary. So whatever this measure of angle A is and the measure of angle C, I said supplementary, they're complementary. They should add up to 90. Now, I don't know what they are. I don't know if A is 70 or if A is 60 or if it's 12. So I'm going to do this generically, and I'm going to say, well, A is just some measure X. And if I'm going to call A X, how about I just call C Y? I'm just going to call one X, one I, and Y. And I know that X plus Y is going to have to be 90 degrees because they account for the remaining 90 degrees of this triangle. 90 degrees is here. So to get to 180, these two have to add up to 90. So I'm going to start with that. I know A and C, I'm going to label those as X and Y. But then what happens if I drop an altitude from B to this hypotenuse? And when I do, we have a situation that looks like this. Now, A and C are still X plus Y, and they still are complementary. They're going to add up to 90 degrees. But let's look at this right triangle on the right side of this, the triangle BDC. And if I block out this triangle on the left and I look at this triangle, I now have a different right triangle with two different acute angles. And these two angles right here, whatever that angle is, it must add with Y to get 90 degrees. Well, we've already established that X is the angle that goes with Y to get 90. So this angle right here on this side of the altitude must also be X. And similarly, if I know that X plus Y is 90, come on, I want to pull, you're not going to let me do this, are you? All right. So if I know X plus Y is 90, then on this triangle, I also know that that angle must be Y. So we have a bunch of angles X and Y. They are complementary. And I can now see how all of these angles compare to each other, which ones are congruent and which ones are complementary. And with that, I can now set up my similar triangles. And I'm going to start with my big triangle, ABC. That's my big triangle. And in my big triangle, I notice that angle A is marked with an X, angle C is marked with a Y. And if I want to see how that is similar to, and I'll just pull this triangle right here. If I want to compare that to the triangle BDC, I'm looking here. And in that triangle, if I want to make my similarity statement, you have to remember that the angles that are congruent must be in the same position in your similarity statement. So if A is marked with an X and C is marked with a Y, then my first and my third letters must also be marked with X and Y. So in this triangle, X is at B, Y is at C, and D must be the one in the middle. And so I'm looking at my X and my Y, and I'm using that to know how I'm going to arrange these in a similarity statement. Well, I can also compare my big triangle, ABC, to that small triangle on the left. So I'm going to get rid of this highlighter, I think. Work with me. There we go. And if I want to look at this triangle on the left side now, I want to look at triangle ABD, and I'm going to do the exact same thing. On the left side, my ABC triangle, A is marked with an X, C is marked with a Y. That means, that definitely looks like an X. That's a Y. That means that on the right side, my first and my third must also be X and Y. And in this blue triangle, A is my X, B is my Y, and D, the right angle, is going to go in the middle. And so now I've compared my big triangle to each of the two smaller triangles created by the altitude. but we can also compare the two smaller triangles. So now I'm going to compare the one on the left to the one on the right. So I'm now going to compare yellow to blue. And when I do that, I will have triangle. On the left, you can start with whatever you want. Let's do a ABD, triangle ABD, my blue one on the left. And I'm looking at those angles. A is X, B is Y. That means that when I name my triangle BDC over here, I have to make sure that the first two vertices are the X and then the Y. The X in the yellow triangle is B. The Y in the yellow triangle is C. And then the right angle D is going to be the last one. So there's how you can figure out the similar triangles on your own without having to just memorize those formulas. And we're going to do that one more time with these two. I'm going to do these two real quickly. I'm going to do the exact same thing I started with. I'm going to say, well, I don't know what the acute angles are in my big triangles. I'm going to call that X. I'm going to call this one Y. And if those are my acute triangles, then in each individual triangle, you must also have an X and a Y. So if this one is Y, this angle on the right side of the altitude would be the X. The one on the left side would be the Y. And then as I start to name my similar triangles, I'll start with MQP. And I notice that in triangle MQP, my acute angles M and P are my X and my Y. And then when I compare that to the two small triangles, so let's look at the one on the left, I need three letters. My first letter needs to be the X, that is M. My last letter needs to be the angle marked with the Y, that's up here at Q. And the right angle M must be in the middle. Do the same thing to get the similarity with the triangle on the right. M is my X in my big triangle. So the left side, I'm starting with the X. So the one on the right, I need to start with the X angle. That's Q. I need to end with my Y. That's P. And that's also P for the QNP triangle. And then the right angle of N goes in the middle. And then when I compare the two smaller triangles, I'm going to start on the left, and you could call it whatever you want. I think I'll call it MNQ. And so if I look at triangle MNQ, M is my X, Q is my Y, which means when I name the triangle over here, the QNP, I need to start with the angle marked with an X, that's Q, and I need to end with the angle marked with a Y, that's P, and then the right angle N goes in the middle. And so there's your similarity statement. And then from that, you can set up your proportions to solve for any unknowns. I don't think I'm going to do number two. Number two works out very similarly, and I think we did that one in class anyway, so you can go back to the notes from Friday to check that out. So let's look at these problems, and for these, because it does get repetitive, I'm only going to do number 5. And so I blew up number 5 right here. And again, it helps if you want to, I guess you don't have to, but it helps if you set up your similar statements. And I've been using X and Y. However, X is already claimed, and I'm worried I'm going to confuse myself if I label my angles X and Y. So in this case, I'm looking at my big triangle. I'm ignoring the altitude, KM, and I'm looking at my big triangle. I'm going to call the acute angles A and B. So if I call my acute angles A and B, then in each of the smaller triangles, the acute angles must be A and B as well. And so I do that. And I'm trying to set up some type of proportion, some type of similarity statement that will allow me to solve for X. And I have to choose. Do I want to use the big triangle or do I want to use both small triangles? And I noticed that in my big triangle, if you ignore that altitude, I have all 3 side lengths of the big triangle. It's a good old 5, 12, 13 right triangle. So I definitely want to use the big triangle. So in my similarity statement, I'm going to start with JML. And then I am going to make that similar to, and I'm looking at my small triangles. First I'm going to do this. In my big triangle, J is my A angle and L is my B angle. So when I set up my similarity statement, I want to make sure that I keep my angles in the right position. And I don't think it matters if you want to use the big one, JMK, or if you want to use the little one, MKL. I like the big one. It's easier to see. So I'm going to go with that one. And in that the bigger triangle on the left side here, J is A, J is still A there. And then my third one needs to be my B angle. And in the triangle JKM, M is the B, K is the 90-degree angle. And so there's my similarity statement. And I am solving for KM. That's my X. So I look here, this is where X is. So I absolutely must connect KM to ML. So I'm going to do that. X over ML. And ML is right here. That's 5. Equals. Then I'm looking at my triangles, and instead of just randomly choosing, I'm looking at my triangle JKM, and I notice that I have the length JM. JM is first and third, so I'm going to connect that to first and third of the big triangle. So I have X over ML is JM, which is 12, over JL, that's the first and third of the original, that's 13. And now we finally have a good old proportion that we can cross multiply and solve. So I have 13x is equal to 60, and then we'll divide by 13, and I get 60 divided by 13. And so there is your answer for x on number 5. Let's see, I'm going to move on. Moving on. And I'm moving on to geometric means, and this is where 6th period we didn't even sniff this in 6th period. So 7th period, if you're watching this is going to be a little bit of a review, which is good for you. 6th period, you definitely need to pay extra close attention starting here. The geometric mean is different than the arithmetic mean. In previous years, anytime you heard the word mean, you probably thought add the numbers and divide by however many numbers there are. And that is a mean. That's arithmetic. The geometric mean is different. It's there's a geometric mean of 2 positive numbers, and that is the number x that satisfies this equation. A over x equals x over b. Now that does work its way down to, if you cross multiply, x times x is x squared, a times b is ab, and then if you solve for x, you get x equals the square root of ab, and that really is what you need to remember for the geometric mean. X is the square root of the product of the 2 numbers. Now you can set it up, if you don't want to memorize that, you can set it up as a proportion, a over x equals x over b, but these are 3 different representations of the same equation or same fact. And in the case of a right triangle with the altitude drawn, you have some geometric mean situations. And these can all be proven, if you wanted, with similar triangles. You can set up your similar triangles, but there are certain relationships that show up enough that we could just memorize a generic setup without going through this process of connecting similar triangles and determining which side lengths we want to use in our proportions. And so one of them, the altitude A, I'm going to just circle it. So we have the altitude A. The altitude is the geometric mean of the 2 pieces of the hypotenuse. So S1 is this piece right here. S2 is this piece right here. A is the geometric mean of those. And so you would set that up if you want to solve for that altitude and you happen to have those 2 pieces. It's S1 over A equals A over S2, and then you can cross multiply and solve. It also turns out that if you have the legs of the big triangle, notice they are L1 and L2, leg 1 and leg 2. They also create a geometric mean situation. And so let's look at L1, this first piece right here. We're looking at L1, and it is the geometric mean of, and it goes back to the original hypotenuse. It's the piece of the hypotenuse that touches L1. So notice it's S1 over L1 equals L1 over the entire hypotenuse. So it's S1 over L1 equals L1 over the whole hypotenuse. And we follow that exact same trend for the other one. If we're looking at L2, now we're going to use the piece of the hypotenuse that touches L2. And it's L2, or S2 over L2 equals L2 over the whole hypotenuse. And so there are a couple of geometric mean situations where if you can recognize that those are the pieces we have and where the variable is, we can skip the similar triangles and go based on those proportions. And so this next page, let's see, we're finding geometric mean of 2 numbers, and then we'll come back and we'll tie it to the right triangles with altitudes. So the geometric mean of a pair of numbers And we're going to now simplify answers. We're not going to give decimals for radicals anymore. I do expect you to simplify them. And the geometric mean is the number x. Now, if you want to set it up as a full equation, it's 3 over x equals x over 48. But that will always turn into x squared is 3 times 48. And x is the square root of the product of those two numbers. Square root of 3 times 48. And so I'm okay if you want to. You can jump straight to that line right there if you know the geometric mean setup. And 3 times 48 is 144. And so the square root of 144 is 12, which means the geometric mean of these two numbers is 12. Now, again, don't confuse that with arithmetic mean. The arithmetic mean is 3 plus 48 divided by 2. We're not doing that. We're doing geometric means, which is the square root of the product of the numbers. I'm not going to finish number 8, but number 8 is the square root. The geometric mean is the square root of the product of the square root of 24 and the square root of 6. So we have like a lot of square roots going on there, but that would be your setup for the geometric mean on number 8. And then here we are going back to geometric means and tying it to a right triangle with the altitudes drawn. And so we're just going to answer these real quickly, and they're just going to be generic. We just have letters A, B, actually, no, what is it? E, F, G, H, J, and D. That's interesting. Oh, D, whatever. All right. So J is equal to, and this one is the hint is the addition. We'll just say G plus H, and that's good old segment addition postulate from way back in the day. The altitude is the segment drawn from the original right angle to the hypotenuse, and it is perpendicular. That is E. The legs of the triangle, and here we're talking about the legs of the big triangle, because depending on your interpretation, there are other legs as well. We're looking at the legs of the big triangle. That'll be D and F. The hypotenuse of the big triangle would be the length J, but we've already established that J and G plus H are the same. And here we get into the geometric means. E, the altitude, is the geometric mean of the pieces that of the hypotenuse the altitude creates. So E is the geometric mean of G and H. F, now we're looking at a leg. F is the geometric mean of, and these are the geometric means of the piece of the hypotenuse that touches F and the whole hypotenuse. So H and J, or as we established, J is the same thing as G plus H. Are we good? Okay, moving on to D. Now I'm over here looking, where's my eraser? There he is. Now I'm over here looking at D. D, that's the leg, and the leg of the big triangle is the geometric mean of the piece of the hypotenuse that touches it. And so we're looking at G and the entire hypotenuse, which is J, or once again, we could say G, and we know that J is G plus H. And then 16, 17, and 18, we'll finish setting these up. G over E. And so we're looking at E. E is right here. And E is the geometric mean of G and H, which means G over E is equal to E over H. Number 17, D, we're looking at this piece. And D is the geometric mean of the piece of the hypotenuse that touches the leg and the entire hypotenuse. So we have G over D is D over the entire hypotenuse J. Or if you really wanted to, you could say G plus H. And then finally, we are looking at F here. That's the leg we're looking at. H over F would equal F over J. And again, you could say F over G plus H. Cool. So there's how we will set up our proportions in those, whether you're looking at the legs of the original triangle, the big triangle, or the altitude. Okay, let's put a couple of these into practice. We're solving for X in these. Well, number 22, we're solving for Y. And so X, I notice we have the altitude, and the altitude is the geometric mean of the two pieces of the hypotenuse that the altitude creates. And so I would say 7 over X equals X over 9. X squared is equal to 7 times 9, which is 63. X would be the square root of 63. And honestly, it would have been better not to even multiply the 9 and the 7, because now, as I attempt to clean up the square root of 63, I want to find a perfect square that divides into it, and I already see the 9. The square root of 9 is 3, square root of 7, and that would be your value of x, 3 square root of 7. Number 20, we once again are looking at that same altitude. We're looking for the altitude, which is the geometric mean of the pieces of the hypotenuse it creates. I have one of them. We need to find this other one right here. If the whole hypotenuse is 100, then this piece of the hypotenuse is going to be 100 minus the 36 on the other side. That is 64. So we will now do the geometric mean with x and 36 and 64. And so I'm going to show you a little secret here. X, nope. I'm going to do 36 over x equals x over 64. And I notice that those two are perfect squares. So I am not going to multiply those. I'm going to leave it as 36 times 64, because the square root of 36 and the square root of 64 are both nice. X ends up being 6 times 8, which is 48. Cool. We're going to skip 21. 21 works. Oh, no, it doesn't. That's a leg. So 22, we have the leg. And now, remember, the leg is the geometric mean of the piece of the hypotenuse that touches it and the entire hypotenuse. So here, I wasn't given explicitly the length of the entire hypotenuse, but if this is 3 and that's 8, I know the entire hypotenuse is 11. And so I would set this up as 3 over y equals y over 11, and we'll turn this into a y. And we get y squared equals 33, and y would be the square root of 33. And the square root of 33 does not have any, or 33 does not have any perfect squares that go into it. So there is your answer, the square root of 33. Let's see, moving on. 23, we have an x and a y. And let's see, I'm going to solve for y first, because I kind of like doing this one for like the geometric mean involving the altitude of the triangle is easier for me. And so that will be 4 over y equals y over 5. Remember, the altitude y is the geometric mean of the pieces of the hypotenuse it creates. So I set that up. We get y squared equals 20. Y equals the square root of 20. And the square root of 20 cleans up to 2 square root of 5. So there's my y. Then to solve for x, we actually have some options here. I meant to start with 24. I highlighted 24 to remind myself to do that one. Whatever, I'm already in on this one. If I have y, we have a couple of options now to solve for x. I could ignore the fact that I know what y is, and x, because that's a leg of the big triangle, is the geometric mean of the piece of the hypotenuse that touches it and the entire hypotenuse, which is 9. So I could solve for x on 23 by doing 4 over x, the piece that touches the leg over the leg, equals x over 9. X squared is equal to 36. And boy, that's nice and clean. X is 6. X is 6, and that works. However, once you have solved for y, if I know this side length right here, if y is 2 square root of 5, I could look at only that triangle on the right side, and I now have the legs of a right triangle, and you have the option of going Pythagorean theorem with just that right side of the triangle. So there are other ways to do this. Now, I believe that the way I did this is easier because 4 and 9 are integers. You're not dealing with a square root. But if I did have a nice number, like if y ended up being 6, I would probably just go with Pythagorean theorem with 4, 6, and your hypotenuse x. So just kind of weigh your options and look at what you have. Let's see, number 24. We need to solve for x, y, and z. And let's see, so I'm looking here. The easiest one to solve for first, I think, is going to be x, because I can get x. I can completely ignore the right side of that triangle, and I can get x here with just the Pythagorean theorem. If this is x, that's a right angle. I know that 2 squared plus x squared equals 4 squared, and we can solve for x with that. That's 4 plus x squared equals 16. x squared is equal to 12, and x equals the square root of 12, which cleans up to 2 square root of 3. So my x is 2 square root of 3. And now that I have the x, we have so many options here. We cannot solve for z. No, you can't solve for z yet. I'm going to solve for y. And our options to solve for y is, I know the altitude is the geometric mean of 2 and y. So I could say 2 over 2 root 3 is equal to 2 root 3 over y. That would work. And I can cross multiply. 2 times y is equal to 2 root 3 times 2 root 3. And if you remember, when you multiply that, 2 times 2, you can multiply the numbers outside. 2 times 2 is 4. Root 3 times root 3 is 3. That's 12 divided by 2. 12 divided by 2 is 6. And now I know that y is 6. And now that I have y, I can get z with a whole lot of options. I can either do Pythagorean theorem with a big triangle, because I know the entire hypotenuse is 8. Then I could say 4 squared plus z squared is 8 squared. I could, and I'm going to do this just to reinforce the geometric mean concept. The leg of the original triangle is the geometric mean of the piece of the hypotenuse that touches it, which is 6, and the entire hypotenuse, which we now know is 8. And so I'm going to set it up that way. 6 over z is equal to z over 8. Cross multiply. Z squared is equal to 48. Z equals the square root of 48. And I know that 48 is 16 times 3. I can take the square root of 16 out. Square root of 16 is 4. The square root of 3 stays in. And there is my z. 4 square root of 3. Cool? Cool. And I think for the sake of time, we're already at 26 minutes, 27 minutes almost. For the sake of time, I'm going to stop there. The rest of the problems are just variations of that, choosing what pieces you have and what you want to do to solve for all of the unknowns. So I'm going to stop there, and hopefully that made some sense. I think it was a little bit smoother than what I attempted to do Friday, and we will polish this up before our test Thursday.